they can use the rate at zero position. So when you talk about the order of a reaction, you can't get it from the equation. It means these numbers are actually coming from some type of experimental detail. The first method says you draw a concentration time graph by the initial rate method and the half-life method. You have to copy this.
Okay. Okay, I've copied.
Right. Now, what is initial rate method, which I mentioned that you can draw a tangent as mentioned. Actually, a chemical reaction occurs at a decreasing rate. Normally, the rate is maximum at the first instant, but gradually the rate decreases. So what we do, we draw a tangent on zero position, and then we follow the rate from there, determining the initial rate of the reaction. So give the
Yes.
heading initial rates method and copy this screen.
Yes. I've copied.
Now look at this graph, and we did one question, I think, in the last class
Yes.
when we shared the file, and we have
Yes.
drawn the correct tangent. The tangent drawing is needed very accurately, and then this type of data examiner will give in the paper that, for example, RBR is reacting with NaOH and it's forming a ROH plus NaBr. The order of reaction may be deduced by plotting the graph of one component, for example, RBR, against time. This type of data will be given. Even though it looks a bit strange, but we have questions where examiner go for a pure mathematical exercise. I think we did one question on that also when it was in Equilibria and he was asking to draw a graph. Here, the problem is there. You need much more accurate graph because you have to draw a tangent. In maths, tangents are always sensitive to minor changes because if the tangents slightly shake, the, the answer changes a lot. You can see here, there are two curves.
Yes.
There are two curves like this. There are two curves. There are two curves which are coming down and the dotted lines are showing the two tangents. Now, this is how we draw the tangents on the two concentration. You have to write after that. You have to
Yes.
copy this screen. I'm just coming, copy this screen.
Okay.
So in
On
this method,
this graph,
yes.
it's only for one reactant.
This is actually A and B are constant. So I have two runs of one. You can't actually, this is A1, A2. So I'm keeping B constant. Ideally, this is the best method. Do not plot both the reactants on one, because definitely then it will be a problem to make the judgment. But it is possible to draw two separate reactants on one. But presently, I am keeping B constant and I am running A twice, changing the concentration of A twice and plotting them on the graph.
Okay.
So what is the method that you have two concentrations? You can run the two graphs together. Here you have A and B OH, both are OH, but two separate concentrations. We start with two separate concentrations of OH and we follow the reaction by changing concentration of OH. On regular intervals, we have recorded the concentrations of OH and then we can plot it. Now give the heading half-life method. Now copy this screen.
Okay. Yes. I've copied.
Half-life is the time in which the original concentration becomes half. So if you follow a reaction, this method uses concentration versus time sketches. First order rate versus concentration. What's happening? When you have a first order reaction, rate and concentration are directly proportional. So when you draw the graph, look at this. First you copy this, update this screen.
Okay. I've copied.
Right. Now, when you talk about first order reaction, rate is proportional to concentration. So you will plot a concentration time graph and concentration of the reaction as it proceeds. Now, what you do from the 4, from the value of 4, you will come down to 2 because you are looking for the half of concentration. And then you go and read the time. This time is called half-life in 17 minutes. This number is called 17 minutes. This is called half-life, then another half-life, then another half-life. This is how we read the graph. So we will note for every half on concentration and the corresponding time. This is called half-life concentration. And then we have a formula in our course. We put the half-life in the formula to get the rate constant from the equation. This is only for first order. So after copying this, you have to copy this screen.
Yes. I've copied.
This is the first order, and look at the time. Half-life is constant and half-life is not changing. This is a special feature of a first order reaction. Half-life is constant. So when you take the first order, you can read it from the graph, like this is a graph.
Yes.
Okay. This is a topic which you might have done if you had done, you have definitely have done maths in O level. And we have a
Yes.
concept in our O level statistics. The concept was finding the median from a statistical graph. And we used to solve this for finding median. Median is a concept of making the number half on y-axis and then read it from the x-axis. So suppose that you put concentration on y-axis and you put time on x-axis. The graph always comes down. This is the property of regular reactions. The graph comes down like this, but it never touches x-axis. It touches y-axis, but it does not touch x-axis. So you copy with me.
Okay. I've copied.
So we need the concentration and then we half the concentration.
Yes.
Now this time is called T half. You have to update the same sketch.
Okay.
This is called half-life.
Yes.
So what is half-life? It is the time concentration of the reactant becomes half of its original value. The time in which the original concentration becomes half. So this is a graph, and we can find the half-life, and we can notice here that half-life is constant.
Yes.
So write under it.
Okay.
Now this is the formula. P half is equal to ln2 upon K. K is the rate constant. So you have to give a side heading
Yes.
formula. And then you have to copy this screen.
Okay. Okay.
Now look at this calculation. ln2 is 0.693. So you can see, look at the graph. You can see on the graph. And I'm taking 17 minutes from the graph, which is the half-life, and putting here. So this calculation is based upon the graph you can see here.
Yes.
Now, second formula, which is also coming from O-level physics, actually, x upon x naught is equal to half power n, where n is the number of half-lives, and you have to copy this.
Okay. I've copied.
Right. Second order reaction. When we talk about a second order reaction, look at that. Half-life is not constant. In a second order reaction, half-life actually increases gradually, and it means that half-life is not constant. Half-life is constant for first order reaction. First order reaction creates always a smooth curve. So give the heading second order reaction.
Yes, I've given.
So write under it that half-life is not constant generally it increases.
Yes.
Now, this is a version here. The formula is T half is equal to 1 upon Ka. You have to copy this screen.
Okay. Okay, I've copied.
Okay, good. Now, what is a zero order reaction? A zero order reaction is that which is whose rate is independent, whose rate is independent to the concentration. So what is a zero order reaction? First, we recall the zero order reaction is independent to change in concentration.
I've written it down.
Good. Now look at this one. The gradient is minus K. There is no trend. Technically, with the half-life, there is no trend. So we have to copy this.
Yes. I've copied.
So, so when we talk about half-life, we can use these type of data, and you no need to copy it, but you have to read it. First order reaction of catalytic decomposition of H2O2. H2O2 decomposes into H2O plus O2. Now calculate the half-life of the reaction. You can read it directly from the graph. Just write down the answers. We can discuss them.
Okay. The half-life of the reaction will be 10.
Good. Show that the reaction is a first order reaction, which you can prove by
The
proving.
half-life,
Yes,
it's
please go.
constant. The
Half-life
half-life is constant.
is constant. Very good. Now, third part.
It will also take 10 minutes.
Hmm.
Or do they mean in total?
How long will it take for the concentration of H2O2 to become 0.25? You're talking about part 3.
Yes.
So it's not looking possible from the graph. I think we can do it from the calculation, from the formula, because it's a
Oh.
first order reaction. So we have the formula because it's not a proper graph.
Mm. Okay. Well, it's be 0.0625 minutes.
Using the 0.025, right?
Yes. Yes.
And you're using the formula, this one, K is equal to ln2 upon T half.
Actually, I used the other one.
Other way,
X over X naught is equal to.
because it doesn't have, because I was thinking that, right, you're right. Then it's fine. Look at this question. The first order reaction has a half-life of 5 minutes. If the initial concentration is 1.2, what will be the concentration be after 20 minutes? So read the question, make the data.
I'm getting 0.75. Oh, I made a mistake. Okay, I got it. Sir, are you talking? Because I can't hear you.
Have you copied this?
Yeah, I've copied.
Using graphs of rate against concentration. And I thought that maybe I couldn't communicate because there's an issue with the mic, perhaps. That I will send this picture and you can draw this graph and then we can discuss it. That will save our class time because graph drawing, and you can draw on a graph paper and then we can discuss this question.
Okay.
Step 2, using graphs of rate against concentration. Now, how we can draw a graph of rate? Rate is the gradient of concentration time graph. So after giving this heading, write under it that rate is the gradient of a concentration time graph. You have to copy this.
I've copied.
So first, we cannot determine the rate directly because the same issue, rate is not a constant for a reaction. So we need to draw tangents. And for example, there are three runs. There are three runs of a reaction. So we can run it again and again. For every time we take that readings of concentration, repeated reading of concentration, and plot a graph like this. Now the issue is there that there is no one rate, not even with a run one will have multiple rates, rate will decrease. So for every run, we will find the initial rate or any rate which examiner has specified. Otherwise, at t is equal to 0, we will draw a tangent and we will find the rate for every reaction. So then right under it, different runs are made for one reactant. Different runs are made for one reaction. Then you have to copy this screen.
Yes. Yes, I've copied.
So we will draw tangent at time t is equal to 0.
Mm.
So this is how we will draw a tangent. Tangent is always, tangent should always be touching at one point on the graph. And this is the challenge always in a real paper.
Mm.
I have drawn one tangent. So now you have to draw with me.
Okay. I've drawn as well.
Yes. So this will be in the paper. It has to be very accurate.
Mm.
Then we draw a table of rate and the starting concentration, and we calculate the, for every run, we note the starting concentration and the rate obtained from the initial rate method. So now you have to copy this table.
Yes. I've copied.
Then you plot a graph of rate against concentration. Then copy this.
Yes. I've copied.
So these are the three rates of reaction. Rate of reaction versus concentration. These are the three graphs. Once you plot this graph, there will be a possibility of any of these shapes. Then the horizontal line, when the line is horizontal, it should be zero order. Why it should be zero order? Because it means rate is not changing with concentration. When it is a straight line, it means the rate is increasing proportionally with the concentration. And when it is a curve, it is a second order because rate is moving with the square of the concentration. So these are the three important curves. These are the three important curves. You have to copy them. You have to copy this screen.
Yes. Will plotting the graphs be in P4 or P5?
No, actually, this is a good question. It is not necessary where they meet. They can meet anywhere. The main thing is that zero order is a horizontal line. First order is a straight sloping line. And second order is a curve. The three lines is not necessarily meeting at any position.
Okay. I've copied.
So, for example, the case only one reactant is involved. If only one reactant is involved, like decomposition of calcium carbonate or anything like that, concentration against time rate would be changing at 0 and all other positions. So we can take on one graph. We will not draw multiple graph now because there is no other reactant. So we will draw one graph and we will take multiple gradients and we find the rate from each. And then we draw a graph like this. So you have to copy this. This is a special case.
Okay. I've copied.
So we will take one graph this time because there is no other reactant and we'll make a table from here. Just copy this now.
Mm. I've copied.
Good. So we will use one graph, we draw one graph and we take multiple gradient from here. And from that graph, we will determine the value and the unit of the rate. Again, this is the shape of the graph to remember. When the line is horizontal, it is y is equal to k. When it is a straight line, y is equal to x. And when it is a curve, it is y is equal to x square. So just give the heading method 3 using graphs of rate against time.
Okay. I've written.
Okay, now you have to remember this point and we will inshallah continue in our next class. Thank you.
Inshallah. Thank you.